All right. So, hello and welcome everyone to week 10 of interactive live sessions for the course on Computational Fluid Dynamics for Incompressible Flows. The course is being offered by NPTEL, is being instructed by Professor Amaresh Dalal from IIT Guwahati. My name is Debjit. I am a PhD scholar at IIT Madras and I am the TA for this course. So, like every other week, we shall dive into solving some tutorial problems together. Okay. So, without further ado, let's move on. We will move on to question number one of today's session. So, the topic of discussion of this week began with finite volume methods. So, earlier on, we have discussed everything with reference to finite difference methods only. So, the first question is a direct, has a direct connection to that. It is asking us what is the main difference between the finite volume method and the finite difference method. So we are using two different methods. What is the core idea? What is the core difference between the two? So is it option A? The finite volume method discretizes the equation in terms of volumes instead of points. Option B, the finite volume method uses central difference scheme instead of the forward or backward difference schemes. Or is it option C, the finite volume method only works for one-dimensional problems? Or is it option D, there is no difference between the two methods? That is basically none of these. So which one would it be? Take your time and try to figure out the correct solution, which is the what is the core difference between the finite difference method and the finite volume method. There are four options. Option A, the finite volume method, discretizes the equation in terms of volumes instead of points. Option B says the finite volume method uses central difference scheme instead of forward or backward difference schemes. And option C says the finite volume method only works for one-dimensional problems. And there is option D, which says that there is no difference between the two methods as such. Okay, so if we have a look at the solution is option A. The finite volume method discretizes the equations in terms of volumes instead of points. So as we have seen earlier, so let's discuss it in context of 1D only. It extends to 2D and 3D as well. So in finite difference scheme, what we have done up until now, we took points like this. So let's say if ij is our main, not j, let's say for the ith point, we have two neighbors, I plus 1 and I minus 1th points. And then we try to solve for values in these locations only. So these are discrete points over where we try to attain the solution, right? And the philosophy in finite volume method is that there are these control volumes, which are finite volumes within which we are interested in knowing the solution. So they are also in the entire volume we don't know, but let's say in the cell centers of those volumes as well as in the faces of these volumes, we try to figure out what the solution would be. Right. So another issue, another not issue, an added benefit of this philosophy is that we try to conserve a certain quantity within each control volume. So even these infinitesimally small control volumes, we try to uh, conserve whatever physical quantity we are interested in. It could be mass when we are solving for continuity equation. It could be momentum while we are solving the Navier-Stokes equations. It could be temperature. It could be species, some the concentration of some species. So anyway, all of these quantities are inherently conserved by the philosophy of the finite volume method, which is not implicitly done in the finite difference method. There you have to make sure that you are solving the correct conservation equations. Okay. So moving on. So basically, if we go back to the main question in hand, so the main difference lies in discretizing in terms of volumes instead of points. So finite volume method will think in terms of discretizing in finite volumes, and finite difference method would think about discretizing into discrete points. Okay, so I hope that makes things clear. We will move on to question number 2 now. So question number 2 is asking us, what is the purpose of the flux term in the finite volume method? Does it, option A, to represent the rate of change of the physical quantity within each control volume? Option B, to represent the transfer of mass, momentum or energy across the control volume boundaries? Option C, to represent the boundary conditions applied to the control volume? Or option D, to represent the source or sink terms in the equation? So which one would it be? Read the options carefully and try to figure out the right answer to this question. So there are different terms, right, in the equations when we discretize in using any method. For the finite volume method is our focus right now. So over there, one of the terms is the flux term. The question here is, what is the purpose of this flux term? What does it represent? Does it represent the rate of change of physical quantity within each control volume? The transfer of mass, momentum or energy across the control volume boundaries? The boundary conditions applied to the control volume? Or the source or sink terms that might be present in the equation? So let's have a look at the solution. The solution is option B, to represent the transfer of mass, momentum or energy across the control volume boundaries. So if we have a two-dimensional control volume like this, and so basically we draw, there are fluxes like this. So let's say this is JW, JE, there could be some JN, similarly JS. I'm drawing only the arrows representing the flux directions. Uh, they have to be taken a dot product with the surface normals at the four faces as well, the face normals, in order to determine the rate at which uh, any physical quantity is being transferred across these control volume boundaries. So that is what the flux term represents. So the flux term is the summation of the you know the fluxes along with flux at faces while taking a dot product with the surface normals of each face. So here F represents east, west, north and south. This is summation over F. Right. So this flux term, this actually keeps count of how much of the physical quantity entered into the system and how much left. The balance of that would be equal to this flux term F. Okay. And the physical quantity could be anything. It could be mass, momentum, or energy, as we talked about earlier. It could be species and concentrations as well. Right? No. So moving on, we will move on to question number 3 of today's session, which is asking us, which of the following is a disadvantage of the finite difference method when compared to the finite volume method? So is it more computationally expensive, option A, or option B, it is less accurate, option C, it is less flexible in handling complex geometries, or is it option D, it cannot handle time dependent problems or transient unsteady problems? Which of the following is a disadvantage of the finite difference method when compared to the finite volume method. So it must be something that the finite volume method can do, but the finite difference method has has a disadvantage in that particular area. So there are four options given below. Read them carefully. It is option A, it is more computationally expensive. Option B, it is less accurate. Option C, it is less flexible in handling complex geometries. And option D, it cannot handle time dependent problems. So let's have a look at the solution. The solution is option C. It is less flexible in handling complex geometries. So the other things, computational expense, accuracy, and time dependent. So the first two are incorrect because it's the same for both. Given you are using the same you know uh, grid size and time step size and all that, they are comparable. There is no huge difference between the two, and accuracy is also dependent on the uh, grid size and the step size, and how you choose them. So those things are comparable, and that is not a huge difference between a finite difference method and a finite volume method. And the option D is incorrect as well because it can handle time dependent problems as well. Option C would be the correct one because finite volume method is more flexible in handling complex geometry. So let's say finite difference method, whatever we have learned. So there we had this regular grids, right? Orthogonal Cartesian grids. Now, once you deviate from this orthogonal Cartesian uh, regime, it becomes very difficult. So let's say you have a bent pipe flow like this, right? So you have a face like this over here and a face like this over here, and you're trying to use CFD to solve for the flow within this. There is a flow incoming like this, and I want to know what is the flow profile coming out of this. For that, I have to solve for the flow in the entire domain. Now, if I try to use finite difference scheme over here and try to you know, generate some grid like this, so let's say this is my uh, ij and this is my ij plus 1. So in a regular grid, I know that in going from ij to ij plus 1, I just have to go add some delta y to its y coordinate and the x coordinate would remain the same. But in this case, as you can see, there is not only a difference in the y coordinate, there has been a difference in the x coordinate as well, and uh, so this would be delta x, yeah. So and that issue is prevalent for all the points in the grid, and so I have to bookkeep delta x's and delta y's between each neighboring points, and on top of that they are not uniform. They can be different from point to point as well. So this becomes a huge bookkeeping issue if I'm trying to use finite difference method. Now, for the same problem, if I use a finite volume method, I will simply break it down uh, into these finite volumes, which will by themselves. Let's say if I focus on this control volume. It can be a regular rectangular shape control volume, or it can be some other shape as well, triangular shapes and hexagonal shapes and all that. But here the bookkeeping issue does not remain. So here what I'll do is I don't care that where the cell face and cell center of the neighboring points lie. I will simply say that all the fluxes coming in and going out, and if there is any source term in between, and there will be a diffusive, sorry, there will be a convective term as well. I will solve for all the terms within this control volume, and I will try to conserve the mass flowing through it and the momentum flowing through it. That's it. So in doing that, the disadvantage of handling complex geometries is completely bypassed when we are using a finite volume method. The bookkeeping issues become very simple. So that is the main reason why in all CFD applications where the geometries are complex, we employ finite volume method. That is the more industrially prevalent technique. Finite difference method is hardly used, right? So that is the reason. I hope that makes things clear. We will move on to question number 4 of today's session. So, which of these terms need a surface integral? Is it option A, diffusion and rate of change of terms? Option B, convection and source terms? Option C, convection and diffusion terms? And option D, diffusion and source terms. So, read the question carefully and try to figure out the solution. So which of these terms need a surface integral? Is it option A, the diffusion and rate of change terms? Option B, the convection and source terms? The option C, convection and diffusion terms? And option D, diffusion and source terms. So if I write down the generic conservation equation, so that goes as something like this, that dou phi dou t plus a convection term, that is u dot grad phi, and here we have one diffusion term, that is grad of gamma into grad of p, where gamma is the diffusion coefficient, and we have a source term sp. So this is the rate of change term, I'll write ROC. This is the convection term, this is the diffusion term, and this is the source term. We are all well acquainted with this. We looked at all these earlier. So now, which of these terms need a surface integral? Is it diffusion and rate of change of terms? Rate of change terms? Is it option B, convection and source terms? Is it option C, convection and diffusion terms? Or is it option D, diffusion and source terms? So let's have a look at the solution now. Sorry. Let's have a look at the solution. The solution is option C, convection and diffusion terms. So if we go back, uh, this term, the convection term and the diffusion term, these represent a flux. So let's solve it out. So over here, what I'll do is, let's forget the rate of change term for a while, or let's keep it, doesn't matter. So we will keep it, and here we have the convection term. So let's write it a bit in a different way. So let's write it, we will take the conservative form over here. So I'll put down u inside, and I'll take the diffusion term in this way. Sorry, I'm going sideways. So I have dou phi dou t plus, I'm writing down the convection term in a more uh, conservative way, the conservative form of it. And I'm taking the diffusion term in the left hand side. So here we have something like this and equal to the source term phi. And we will put these two within the grad. So I have u phi minus gamma grad phi. Right? U is a vector over here, and this entire thing I'll represent by J. So basically J is the flux. So ultimately it boils down to dou phi dou t plus this flux term equal to Sp. Right? And while integrating, so let's say I'll now integrate all of this with respect to control volume dou V. So control volume dou V is the volume uh, of the cell, of the finite volume cell that we're using. So we apply volume integral to all of them. Now since this is uh, you know a del quantity, we can use Gauss divergence theorem on this and convert it into a surface integral. So that would finally give us this j dot ds over the surface S, and the remaining terms would remain as it is. So since those are not divergences, we cannot apply Gauss divergence theorem over there. But since we had a divergence quantity here, we simply converted it into a surface integral. So that is why surface integral is needed by the flux term, and the flux term contains the convection and diffusion terms. That is why option C would be the correct answer. Okay, I hope that makes things clear. Let's move on to question number 5 of today's session, which is asking us which of these terms need a volume integral while modeling steady flows. Is it option A, convection term? Is it option B, diffusion term? Is it option C, source term? Or is it option D, rate of change term? So read the question carefully and try to figure out the correct option. So let's have a look at the solution. The solution is option C, source term. That is because recently in the last question we saw that it is the flux term containing the convection plus diffusion terms that need a surface integral. So it doesn't need a volume integral. So that's why option A and option B were out of uh, question. And option D, rate of change term, this would also need a rate of change ROC term, that is dou phi dou t. That would also need a volume integral, but you have to notice this carefully that in the question we had said steady flows. So in steady flow, this would identically become 0 and remain 0. So we don't need to worry about it. So that's why this also goes out of question. It is only the source term that remains, and that has to be integrated over the volume of each cell. Okay. So that is why option C would be the correct answer. Source term is the term which needs a volume integral while modeling steady flows. Simple. So we will move on to question number 6 of today's session now, which is asking us what is the order of accuracy of the equations as a consequence of the mean value approximation. So we make an assumption known as mean value approximation, which is saying that the integral of any quantity over the volume is equal to the mean value of that volume into the volume itself. And similarly, we do the same thing for the faces as well. So we take the mean value at the center of the face, and so using these assumptions, so as a consequence of these assumptions, there is a certain fixed order of accuracy of the equations. So is that order of accuracy first order, or is it second order, or is it third order, or is it fourth order? So that is what this question is asking us. So mean value approximation, this is nothing but something that we already did. So let's say we had an integral like this over this control volume. We simply took the mean of phi into the volume itself, sorry, into the volume. Similarly, let's say at some phase, if I'm trying to find out the flux into ds, I have dot product. So in this case also, I'll take the average value of the flux and multiply it with the surface area. So taking these mean values, these are the mean values, the mean phi and the mean j vector. We assume that this should satisfy the integrated form of them as well. Now, as a result of this approximation, we saw that there is a finite accuracy that is attached with the equations. So, is that accuracy first order, second order, third order, or fourth order? Let's have a look at the solution. It is actually second order. So we saw in the lectures that by uh, expanding phi into a Taylor series of phi, and similarly same thing we can do for j as well or anything else, and then find out that what is the difference between the actual integral and the mean value approximation. There we saw that it is second order accurate. Okay, good. Now let's move on to question number 7. So 7 is a match the following type of question. We have on the left hand column the flux terms and source terms, option A and B, which are different terms which appear in the equations. And on the right hand column we have cell centers and cell faces, which are locations of the grid where these terms are calculated. So you have to match which term is calculated at which location, and find out the correct combination. So the two terms in the left hand column are option A, flux terms, and option B, second source terms. And the right hand column we have two terms that are we have two options, which are option 1 cell centers and option 2 cell faces. So once you match the following, you can get only two combinations, that is option A, A1 B2, and option B, A2 B1. So which combination would it be? Let's have a look at the solution. The solution is option B, A2, B1. That is, the if I have a control volume like this, the source terms are calculated at the cell center, and the flux terms are calculated at the cell faces. So flux at cell face, so I'll write down this J west and J E, and SP was done at P, which is the cell center. So sorry. So source terms are calculated at cell centers and flux terms are calculated at cell faces. Hence, the correct option would be option B, A2 and B1. Okay, simple. So now we will move on to question number 8 of today's session, which is asking us that which type of boundary condition can be most easily handled by the finite volume method. Is it option A, Dirichlet boundary condition? Is it option B, Neumann boundary condition? Is it option C, mixed boundary condition? Or is it option D, flux, periodic boundary condition? So which type of boundary condition can be most easily handled by the finite volume method? Is it option A, Dirichlet boundary condition? Is it option B, Neumann boundary condition? Is it option C, mixed boundary condition? Or is it option C, periodic boundary condition? So let's have a look at the solution. The solution is option A, Dirichlet boundary condition, where we uh, specify the values at the boundary. So let's say if I have a boundary like this, I, I have a 1D domain like this, and I'll draw some more cells for sake of it. So at this boundary, I specify some value. That is the Dirichlet boundary condition, right? So that is simply integrated into the problem and I can move forward with it. Now, if something else is given, like a Neumann boundary condition where the flux is given. So in order to calculate the flux, now I have to, consider a ghost cell like this and then make an approximation of what the flux could be, and as a result of the flux what would be the values at the interior points. But consideration of this fictitious cell or this ghost cell is required. Fictitious or ghost cell is required, and that is the same for all of them, mixed and periodic boundary conditions as well. Only the Dirichlet boundary condition can be simply included in the problem without considering any fictitious or ghost cells. And as you can imagine, this would have to be done in all boundaries. So that is why the Dirichlet boundary condition is most easily handled by these uh, you know finite volume methods. Okay, all right. So moving on, we will move on to question number 9 of today's session, which is asking us that explicit schemes for solving finite volume method are limited by issues regarding what? Is it option A, accuracy, option B, stability, option C, convergence, or is it option D, all of the above? So if I'm trying to solve finite volume method problems by using some explicit schemes, what is the limitation of it? What is the issue which arises out of that? Is it accuracy, stability, convergence, or all of the above? So let's have a look at the solution. The solution is option B, stability. That is because that is the main issue in all explicit schemes, that for any given grid size, I have a limited delta t or time step size which I can use, and that is given by the CFL criterion which I have to follow. If I don't, then there will be issues regarding stability of the problem, which would ultimately lead to convergence issues as well, right? So that's why the main issue is stability, which is conditionally explicit schemes are conditionally stable. So unless we religiously follow the stability criterion, we are going to have some issues regarding the stability of the solution. and that would further downstream affect the convergence and other issues as well. So that's why uh, implicit schemes are more preferred to explicit schemes in order to avoid these stability issues. But then also there are some problems. So that is what the last question of today's session is about, question number 10, which is asking us that implicit schemes for solving finite volume method can use large time step without any stability issue. Then why is time step size kept small in such situations? So in case of implicit schemes as well, we don't use very large time steps. We use a small time step size. Why do we do that? In order to option A, to increase the accuracy of solution, option B, to ensure stability of the solution, option C, to capture the physics at small time scales, or is it option D, that is none of these? So let's have a look at the solution. The solution is option C, to capture the physics at small time scale. So let's say there is some vortex shedding which is happening at a, uh, I have one cylinder and there is a flow over it, and there is vortex shedding happening at a frequency of, let's say, 10 to the power 3 hertz or 1000 hertz. So the uh, time difference between two vortices being shed is of the order of, you know, 10 to the power minus 3 seconds, which is milliseconds. So now, even in this situation, if I include an implicit scheme for solving finite volume method and take a time step size of, let's say, 1 second, I will get correct solutions at each time step. But would that represent the actual physics that is going on? I won't be able to visualize the vortices being generated and being created, and being they becoming unstable and being shed from the attached wake and all that. So I lose all the interesting phenomena going on within the system if I use a large time step. So in order to resolve that, I need to use a time step size at least lesser than 10 to the power minus 3, preferably even lower. So if I can go to 10 to the power minus 4 second, maybe I'll be able to view all the events that is those are going on. So that is why in all these situations, it is the physics of the problem that determines the time step size which I will choose. Okay. So these are things to keep in mind. Like, stability criterion is not the only thing that has to be kept in mind while choosing the time step size. The ultimate goal is to capture the physics, to visualize whatever flow physics is going on. And in order to do that, my time step size has to be at least smaller than the smallest time scale of all the phenomena that are going on in the flow domain. So these are very interesting issues, and uh, I am personally very excited about them. Okay, so that brings us to the end of today's session. It's been a great session, and thank you for listening to it. Thank you.